Chào các em nha.
Chào thầy ạ.
Chào thầy, thầy chào em. Rồi, hy vọng sau khi quay trở lại các em sẽ tập trung vào việc học.
Học quân sự xong vẫn chưa tập trung nổi thầy ơi.
Chưa hả?
Chứ
Vẫn vẫn đang còn có gọi là tinh thần vui chơi hả?
còn đi học vui nhưng mà có chơi đâu.
À đấy hả? Đi học vui đúng không? Vậy tốt rồi. Thầy dặn nha. Các em chuẩn bị seminar để hai buổi cuối là các em trình bày seminar nha. Đấy thì thời khóa biểu hình như là với lớp các em là thầy nghĩ chắc là còn 3 buổi học lý thuyết, là 1, 2, 3 ở đó. Các em học buổi hôm nay này thêm 2 buổi nữa. Đấy, là mình sẽ học lý thuyết. Sau đó thì các em sẽ trình bày seminar nha. Đấy, thầy có hiệu chỉnh thông báo ở trên e-learning. Thầy có dặn là các em khi chuẩn bị PowerPoint mà chúng ta có thể chia thành nhiều 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 phần khác nhau, mỗi bạn sẽ trình bày một phần nhé của bài nói. Trong quá trình triển khai, thầy thấy có một số bạn hỏi thầy là mỗi bạn trình bày 4 phút là trình bày từ đầu đến cuối hay là hay là như nào, thì thầy có nhắn rồi, là tức là một bài thì nó có thể kéo dài khoảng quanh 20 phút, nhưng mà mỗi bạn sẽ trình bày một phần nhé, một phần. Đấy, thì mỗi bạn trình bày cho thầy khoảng 4 phút thôi là được. Thế thì bạn nào trình bày thì mới có điểm nha các em. Rồi thầy hiện tại thấy lớp mình mới có 25 bạn truy cập. Thì thầy nghĩ là mình phải tăng tốc làm sao cho các em kịp phần lý thuyết. Ờ, mình học online hết kỳ, đúng rồi. Vân ơi, học online hết kỳ nha. Các em sẽ học online hết kỳ này luôn đấy. Vậy là các em cũng trình bày seminar online, cũng là ở trên Google Meet này nhé. Các em sẽ tức là share cái PowerPoint, rồi xong cái trình bày cái phần mà mình được phân công ở trong nhóm nha. Rồi bây giờ thầy sẽ share bài giảng, rồi xong thì để thầy ghi lại cuộc họp nhé. Okay. So today we move on. Okay. Part of quantum mechanics. Say we will find Schrodinger equation to describe the behavior of any system of particles. Okay, so this one we should keep in mind the system or object of study. That should be system of particles. Okay, so for example, system of electrons, system of protons, or system of neutron, or system of okay, we say several atoms. So usually the system having small size like nano size and then we can use Schrodinger equation to describe the response of system to what excitation. So I think you already learned last time. We just try to search for the language. We say correct language to describe the system of particles. So, for example, in classical mechanics, or we say Newton mechanics, we select the displacement, x, displacement x, as the language to describe behavior of spring pendulum. And the displacement should be the solution to equation of motion. So equation of motion, this means you will use the Newton's second law, F equal ma, and then you can build the equation, say m and then a equal minus kx. So that should be equation of motion, right? So if so, equation of motion, you will find x, and then from x you can calculate velocity or speed of system, and then you can calculate kinetic energy, potential energy, and then total energy of system. So everything should be very similar. However, in previous lecture, we learned from the Bray hypothesis that if the light, we talk about the light, light has both wave and particle property. So light has wave property shown by interference and diffraction, right? But particle property of light, that is when we assume the light consists of photons, then we could succeed in explain many experimental data. So it means light has both wave and particle properties. So the Bray stated that if the nature is symmetric, and then what property we already knew for the light, now we can borrow to matter. So matter is any substances in this world. So substances will consisting of particles. Originally, we should know that, but in some cases, the matter also show wave property, and we already proved by several experiments, right? So it means if particles show wave property, and then we can describe particles by using wave function. That is the key point, very important. So we already know how to select the right language to describe small particles like electrons, protons, and atoms. So, start from the wave function. Wave function for any free particles like this depends on time and also position. So now if you separate part depend on time and a part depend on position, and then you combine psi zero with the exponential function depend on position, you will note become the wave function depend on position, and then this part depend on time. So we did something like the opposite procedure when we borrow the knowledge from the light to particles. Therefore, we know the form of the wave function, right? This is the form of wave function. But which equation will dominate this wave function? Or if we have a equation that if we solve, we should find this solution, right? But we don't know the form of the equation. We don't know yet. In classical mechanics, we have Newton's second law. Therefore, we can build equation immediately, and then after solving equation, we should find solution. However, this time we just don't know equation, right? We don't know yet the equation, but we just know, okay, the solution. We know the wave function. So we have to do something like reverse procedure so that we can find, okay, equation. Probably at the end we should find the equation look like this, and this one is called Schrodinger equation. But how to do it, how to find this equation, and then we have to, okay, calculate derivative of the wave function with position. Okay, calculate derivative with position, and then even we can also calculate derivative with time, wave function with time. So the language, the mathematical language, when we calculate the change of the, okay, a function with time, it means we know, okay, the state of system described by the wave function. So if we calculate the change of wave function with position and time, and then we understand the response, okay, of the state system with the position and time, right? So very similar to Newton mechanics. If you calculate dx over dt, it means derivative of displacement with time, then you will know how fast the system change position with time, and then it means we know the speed or velocity, right? So that one usually show how fast, okay, the rate of changing position with time. For example, 1 second, 2 seconds, and then with the position of system already change how many meters, something like that. And the wave function, if we calculate derivative with time, we also have a response of the state system, okay, with time. How fast we can change the state of system with time. And very similar, we also calculate derivative of wave function with position, and then we know how fast, okay, the state of system change with, okay, the location. Should be like that. So here already, okay, shown how to step by step to calculate and then achieve the wave, the Schrodinger equation. However, here when I printed to PDF file, something wrong about this one. It's wrong about the characters. Okay, so this one should be vector r. This is vector p, vector r. So, but vector size change becomes some different letter. So let's ignore this one. But instead, please follow my, okay, guidance, my calculation. Okay. So let me open, then share. Okay, please wait for me. So you already see the wave function for any, remember this is free particle, okay. Why we say free? Because the wave function here we borrow the wave function of the photon, but you know photon usually, photon should be free particles, because when emitted photon on flying and then not. Okay, depends on something position, something like potential. So usually, okay, free particle should be similar to photon wave function. Right? It should be psi zero exponential function I over h bar energy of the particle, okay, and then time t minus vector p vector r vector p momentum. So don't forget p or e should be, okay, parameter show particle nature. Okay, so when you learn the Bray hypothesis, you already see relationship between, okay, e with frequency or momentum, okay, in relation to the, okay, to the wave function. Sorry, wavelength. So this one particle property, but frequency and wavelength should show wave nature. Okay, so start from here. You just calculate derivative with position, and then you, okay, you will see that now you have this part depends on okay, time. Exponential function depend on time, and psi zero should be constant. So you basically you can bring this separate, okay, separated et like this, and then derivative with position probably that take place on, okay, exponential function of position. So now if you calculate this one, sorry, plus sign, minus become plus. So you calculate this one, will give you I over h bar and then vector p, okay, and then exponential function, this one again, okay, this one multiplied by exponential function again. Okay, so you can combine exponential function with this one, and then the result become something e0, and then sorry, psi 0 h bar, and then this is et minus vector p and vector r. Okay, like this. So this one, you know, this would be precise function. Here of course depend on time and position. Okay, so maybe let me write in full that depend on position and time. Okay, should be like this. Okay, this one result should be like this. So but you know, people just try continue calculate the second, okay, or the derivative with position. And then you will, okay, actually you will calculate derivative with position both sides of this one, and then it's now you, okay, you have derivative of I. Maybe I will write something like this. You just take this one, put to here, and then this one you substitute by this, and then now you have this h bar vector p, and then derivative with position. This one is psi, okay, but this one, you know the result, this one equal this, and then it means you have to, okay, have something like this, okay, this one square, and then this one just psi RT function. Okay, so now you have an I square over 8 bar square and then vector p square. You don't forget, right? I square equal minus 1. Don't forget this one. Okay. Therefore, the result will be minus vector p square over 8 bar square and then psi rt function. So we have to say this one is free particle. Anyway, in general, you can, okay, up to this point, you can do something like this. First, you replace d square, okay, and then over dr square. This one by Laplace operator, okay. Usually we write delta. This one replaced by delta. And then psi function RT. How about this one? Okay, so now you have a total energy equal kinetic energy plus potential energy. Okay, always like this. Okay? So if you you know, for free particles, we are talking about free particles. So if free particles, this one equals 0. Okay, so this one is free particle. Free particle. Okay, then U becomes 0, and then actually E equal kinetic energy. But no, kinetic energy in classical mechanics is 1 over 2 mv square vector. Therefore, now you can multiply both okay, numerator and denominator with mass m. Then you can, okay, converse become like this. Okay, this one is 2m. Okay, so this one, it means you will have a vector p square over 2m. So now you see this one actually, okay, you have a p square vectors equal 2me. Okay, 2me multiplied by this one, you have a 2me. So now you can substitute into here, you have something like 2m over 8 bar square and then e and then psi rt. Okay, should be like this. Or you can multiply this one, okay, to here and then divide by 2, and then of course you can find equation look like this. Minus s bar over 2m Laplace operator psi rt and then equal e psi rt. Okay, so this one is we say Schrodinger equation for free particle. Free particle. So it means if you solve this equation, you will find solution look like this. Okay, it will be, okay, this one will be the solution to this equation. However, this is for free particles. How about the system, say particle moving in potential? Okay, so we say particle moving in, okay, potential, in the potential. For that case, of course, EU should be non-zero. Okay, So it means you have a E equal KE plus U. With U is the potential depend on position and non-zero. So in that case, of course, you can take kinetic energy will equal E minus UR. So you know this one actually kinetic energy equal E. So E in this case mean kinetic energy. However, now okay, you also see that this one probably equal to 2m and then ke. We can write like that. So it means you can deduce p square or anyway you can replace this one, replace kinetic energy for this one. So replace E by ke. So substitute into here, it means something like you have a minus 8 bar square over 2m Laplace operator vector rt, and then you will substitute E minus U, okay, vector R and then psi rt, okay. Because the nature of E in this free equation for free particle is mean kinetic energy. So you have to replace this one, kinetic energy, okay, substitute into, okay, replace for E in this equation, and then you will have something like this. So you can change become the form of equation, something like this. So you have this one 0 to left side, and then you will, you can factorize like that. So this one acting on this is acting on this, and then of course you will get this part, and then this part be and then psi rt. So this one actually Schrodinger equation, general Schrodinger equation, depend on both position and then time. However, you can also replace this one with only part depend on position, and then exponential function depend on time, exponential of time will both on left and right, and then of course you can cancel, okay, and then you can have a Schrodinger equation depend on position only. So this one is more general equation, and then of course if you now replace this one by operator, say Hamiltonian operator H, and then you can convert this equation become okay, H with hat acting on psi function equal E and then psi function, okay. So this one is the short presentation of Schrodinger equation, but don't forget Hamiltonian operator equal minus h bar square over 2m delta plus u, okay. So this one is called Hamiltonian operator. Hamiltonian operator, okay. So this we say energy operator. Operator is any mathematical calculation. For example, this guy should include derivative second order with position, but this can be any calculation. For example, integral or multiplying or conjugate, etc. So many possible calculation, usually you call that one in general should be operator, okay, in mathematics. So this one, okay, is Hamiltonian operator that should describe. This one is kinetic energy operator, and then this one is potential energy operator. But for potential, it does a function, a position, so yeah, contain no derivative, no integral, or no anything. So this one simply just one function. This one more complicated, including second derivative with position. So okay, don't forget this one is the Schrodinger equation general form for any particles, okay, in the space, even moving under potential or free move, no problem. Okay, we will use this equation, okay, say Schrodinger equation, to describe any, okay, system of particles. Okay, so this is the way how to receive Schrodinger equation. It's not difficult, okay, not difficult, but you need to perform so that you can, okay, familiar with new presentation. Okay, you see this one already, or this is the kinetic energy operator, potential, and then this is total energy of system. Don't forget to review this part in previous lecture. If you forget, you can watch the video again. I already explained this one is probability density. Okay, so density is mean distribution of something in the space, and then of course this one is a distribution of probability in the space or depend on position. Okay, and don't forget review. Okay, this one, and then this is probability of finding particles if we search all throughout the space, and then it should be 100% or equal 1. Okay, the wave function, if you solve Schrodinger equation, then the wave function should have a many, but only those satisfy, okay, these conditions, then we will select, okay, as the solution to the Schrodinger equation. Okay, review this, okay, from the last lecture. Please do it by yourself. Okay, so after form Schrodinger equation, and probably you will recognize that what you already found. Probably very similar to the case of classical mechanics. For example, Newton mechanics, you select the displacement x, for example, for a spring pendulum. And then you will use the Newton's second law to form the equation. So this one is equation of motion. So after solve it, you will have solution x equal something a equal sine omega c plus phi, something like that. And then after that, yeah, you can draw some figure, and then you understand behavior of spring pendulum. But after that, you can calculate velocity, and then from there you can calculate kinetic energy, and then potential energy, and then of course total energy. Okay. However, in quantum mechanics, you will select the wave function as the language to describe system, but you have to write Schrodinger equation. Right? Now, if you solve Schrodinger equation, you will receive psi function. very similar to displacement, okay? But beside that, you also receive E. E you calculate immediately, okay? Immediately. A little bit different with this. This follow like potential, velocity, and then you can calculate kinetic energy. From X here, you can calculate potential energy. Okay, you take one more step to calculate energy of system. But here, you after solving Schrodinger equation, you receive this together with this. So this one, okay, don't forget solution to the Schrodinger equation is these two parameters at the same time. Okay, this is a different compared to classical mechanics. And then of course, after you find psi function, you can calculate the psi square. This is probability density of searching or finding particles. So something, this is a new one, okay? That probably you will not find probability of finding macroscopic system, right? You never do that. But however, in the case of small system, a system of small particles, usually you have to search for, okay, this one, okay? So don't forget this diagram, maybe, okay? This is good one for you to, okay, to keep in mind that you always show this to find this, and then calculate this at the end. Okay, anyway, okay. Of course, you have to analyze wave function, you analyze energy so that you understand characteristic of system or behavior system. Yeah. It's very similar to this one. You have to analyze, of course. So you also draw the diagram for energy, or you can draw even the wave function. Yes, something like that. Okay. So usually like that, you will understand behavior system based on the figures. Okay. Okay. So after finding Schrodinger equation, then you have to apply Schrodinger equation to different areas. This one is the first example. For example, if you have a one thin film of metal, very thin, okay, very thin film of the metal. You can imagine this is a film, okay, thin film. You can imagine that outside is the air or vacuum. But you know, outside, of course, vacuum, then electron will not stay in the vacuum. Right? It's the reality. So usually you can imagine you have an electric wire at the home and conducting current. Then usually if you stay far enough, and usually you not touch the wire, and then no problem, right? Not get electric shock, because electron basically, okay, not stay in the vacuum, but electron will stay inside the piece of metal. So the question is, how is the behavior of electron inside the metal, and how electron outside of the metal? Okay. So outside here, you can imagine, okay, this one you can see the size of the thin film, right? You see the size of thin film. You can imagine this one, okay? This one is thin film. Outside here is the vacuum. So vacuum, there is no electron stay there, and then of course no wave function, right? Wave function should be zero outside here. And then you don't care to search for wave function because it's already zero, okay, this side. But you have to solve Schrodinger equation to see how is the wave function and then energy, okay, of the electrons when electron moving, okay, inside the the metal thin film. Okay, so that is our target. Okay, so but you probably you will have to use the energy language. This one is the thickness of the film. So thickness, it means from 0 to A. It means the thickness of film is A. Okay, and then if you describe using an energy language, you have a potential for electrons. Right? Electron outside here potential extremely high. Outside extremely high, so preventing electron to move outside, right? So we say extremely high potential, so that electron just stay inside the metal, cannot overcome the barrier to go out, right? So it means potential outside here extremely high. Okay, you draw something like this, extremely high potential. Electron outside inside here cannot overcome the barrier of the potential to go out, right? So that's why electron just stay inside the metal. But inside metal, potential should be 0 because electrons freely move inside the metal, right? Metal surface. So that's why you can write potential equals 0 for the space inside metal thin film. But outside extremely high. So extremely high potential, it means 0 wave function outside. So you just have to solve Schrodinger equation inside the thin film only. Okay. So start from Schrodinger equation, and then now you can let potential equal 0. Then you can solve the equation. But I have to say, we are studying quantum mechanics, and quantum mechanics that's used to understand behavior of system of tiny particles, right? Small size system. And probably you heard about quantum dot. Okay, you have a quantum dot, quantum wire, or quantum well. Quantum well is mean quantum thin film, for example. So you have very small, particle in nano size. So small particle like that will confine electron in narrow space, and you have a quantum dot. Confine electron every direction. Electron cannot exit or go out of the quantum dot or that piece of small material. So you also have a quantum wire, you can have quantum well. And nowadays technology, when you study about high technology, electronic devices, and then of course you should know this concept, okay, very important. For example, LED, LED, also extremely small. You just combine two pieces of material, and then you can make LED to emit the light. And then actually just in nano size, then LED not consume much energy, but it can glow and then give you very well defined color, right? Very good. And then of course we study quantum mechanics to understand and then to predict and also make high technology devices work effectively, right? And then of course one of very important, that is the interaction between the light and material. So how to make material emit the light, and then how material can absorb the light to convert become current, become energy like solar cell, something like that. And then very important to study this topic, and then probably yes, one of the example to understand behavior of electron in this infinite, we say one dimension potential energy well, or electron in extremely thin film. Okay, you have to understand behavior. Start from showing equation like this. If you replace three dimension by only one dimension x, and then potential equals 0 for electron inside thin film, then you can convert become this equation. Schrodinger become this form, okay? And then now if you replace this one by k square, then you expect to have the resolution of wave function should be in this form, both sine and cosine, okay, combined together. So now you have to apply the boundary condition. So at x equals 0 and a, okay, wave function should be 0. At this position should be no electrons, or wave function should be 0. So with this condition, you know, okay, cosine equal 1, and then of course let wave function equal 0, and then of course b becomes 0, okay? So this part will disappear. But x equal a, okay, and then wave function equals 0, you should find wave number should be like this. So substitute this one into here, b0 to here, this disappear, but k after substitution you will find this one. So the calculation is extremely simple, so I will not show step by step how to calculate it. Very simple. Please do it by yourself. Everything already shown on this page. But you know, we don't know yet. We just denote just like amplitude. But how, yes, look like, you have to perform one more step. This is very important. We say normalized condition. That will help you to calculate the amplitude of the wave function. So this one you start from this condition. This one general purpose. You have to take from minus to plus infinity, and then this integral, okay, should give you equal 1. So this one is normalized condition. Okay, so but you know, in our case, the range of that electron can move only from 0 to a, so you don't have to take from minus to plus infinity, but you just take from 0 to a, okay? So the limit from 0 to a psi square function, substitute this one to here, and then perform the calculation, the integral of this. You should find this one. So now let's this one equal 1. Okay, this one equal 1. This is the normalized condition. Must be equal 1. Okay, and then you should find amplitude of the wave function equal this. Now you substitute into here, you get final form of the wave function for free particle inside the potential wave energy, but it means that can be electron inside metal surface. And then start from this setting with k equal this, and then you should find this equal this, and then you should find the energy, okay, of the particle described by this okay, expression. So you can see solution to Schrodinger equation should be both wave function and then energy. Okay, don't forget wave function and energy at the same time. So now, yes, you will, if you want to understand behavior system or of the electrons or particle inside metal, then you have to draw the figure for energy and then for wave function. So as you see here, n can be can take the number 1, 2, 3. So as long as you substitute value n, and then of course you will receive the values. So you have E1 n equal 1, okay? But n equal 2, it means you have a 4 times of E1, okay? This is E2 equal 4 E1. So this one is E3, but equal 9 E1, something like that. The first state is called ground state. Don't forget to this explanation so that you can perform exercise, okay, easily. But the second state will be the first excited state, and then second excited state. So all of the second level go up will be excited state. This one will be the first one. Okay, this is ground state. So what you can see is that the energy here is the discretized level. Okay, discretized level. These characteristics very important, making nano system having high performance. For example, you can make laser with definitely the same color, red or blue, something like that. LED can be definitely good defined color, even red, green, blue, etc. as you want. Okay? Depend on material. And then, of course, when you study material, you see the energy diagram like that, you can predict what kind of color you can create in application, right? So you should not like select randomly or something unexpectedly, but you can select as you want based on your knowledge. So if you are an engineer, of course you should know, right? And then how to design, how to make the LED or something like that with expected color. The characteristic here actually of energy is very helpful, and then should agree very good with the idea of the Planck quantum theory. Don't you still remember Planck quantum theory? What Planck said? I hope you still remember. Planck stated that energy exchange between electromagnetic radiation and material should be in discretized amounts. Okay, energy is discretized into the package. Material absorb one package of energy, and if emit also emit package of energy equal epsilon. Epsilon equal hc over lambda. Right? So Planck quantum theory and photon Einstein theory very important. How this characteristic of energy can support Planck quantum theory and photon Einstein theory is that, okay, don't forget we have electrons. Electron at ground state, okay, very stable, will stay E1. Now if you shine X-ray or the lights or anything like that on the material, electron will absorb photon if only when energy of photon matching with the energy gap here. So if this one absorb photon that having energy gap matching this level, electron will jump to higher energy level. But if electron absorb energy of photon that matching with this level, and then after absorption of photon, electron will jump to higher energy level. So it can jump to higher and then higher. Okay. Electron in excited state not stable. Electron will jump back to lower energy level. When electron returns the state, a lower state, electron will emit energy away. Okay. When emit, this means emit photons, emit the light. That's why, okay, you can generate the light when electron change the state. Right? So it's very important. So probably you can imagine that you have two pieces of material. Now you let the current flow from one piece of material to another one. Then electron from high state will go to lower state when it goes through from one piece to the next piece of material. When electron reduce to lower state like that will emit the light. This is the principle of how to generate the light from current. Let the current flow, electron flow through two pieces of material, but can emit the light. So this one is, have we say technology, for example, LED or laser or whatever, okay? Very similar. Principle should be very similar. So when you study like that, probably you understand very deep, and then yourself can create new system. Okay, new system. So first, you have to say energy discretized. Okay, and then this is a wave function responding to each state is a one wave function. Because n equal 1, then just substitute into here, you have a wave function psi 1. Very similar, you have a psi 2, psi 3, etc. But when you draw the wave function, you see this one go up and then slightly go down, and then actually this one only positive, okay? Positive. You can imagine the dashed line here is 0 value. Now this side positive, but lower we become negative. However, this one no oscillation at all. Okay, this one having oscillation, go from positive to negative. This is having oscillation. This one 1 2 3 like that, you have a more oscillation. Okay, 1 2 3 oscillation, this 1 2 3 4 oscillation, this 5 oscillation. So it means n equal 1, no oscillation. N equal to 2 oscillation. It means you have a 2 maximum. Okay. So don't forget this characteristic of wave function for one particle in infinite potential potential. This one would be very helpful when you answer the exercise. Many questions may relate to this example, right? So don't forget. You always have a note on the wall, note on the barrier. What is a note? Okay, it means wave function 0, and then n equal 2 3 4 5. This should be the number of maximum you have. N equal 1 maximum. N equal 2 maximum, 2 maxima. 1 maxima, 2 maxima, but go to positive, negative side. This 3 maxima. Probably based on that, even you close your eyes, you still can draw the wave function. Okay. This one very important. You will know how many maximum, how many minimum, or something zero. Okay, this one only 1 0 in the middle. Of course, both sides here always zero. Both sides always zero. But based on this one, yourself can draw the figure very quick. Okay. What you found is that higher state oscillation will be higher. Or if you imagine electron inside material will at low state fluctuate little, but higher state will fluctuate more than that, and then faster, also shorter wavelength, right? And then higher and higher level, it will increase the speed, right? When the speed of oscillation faster, and then it means the frequency higher, and then you make electron vibrate harder, and then also can broadcast the wave function to the space also faster. With the wavelength become shorter, frequency higher, and then energy sending to outside also harder, right? Faster, right? So this one is a way of how to sending the electromagnetic waves to the environment, because electrons should be also charged particle, and then when we vibrate like this, and then of course energy sending to outside also fast, right? So I hope you understand the way of people, scientists or engineer doing. Okay. Okay, but so when you keep the surface of metal outside is a vacuum, and then you vacuum can prevent electron go out. It means you keep the potential very high, okay, outside of material. But now if you, for example, you bring one more piece of material closer to surface of the material, and then of course you will reduce the potential, and then my electron can go out easier. Okay, go out easier. So by such a way, you make the potential become finite, adding more material to surface of metal, and then maybe you will have a finite potential. Okay, and then number of energy level will be also finite, but the wave function now you see something different. Okay, let me make comparison. Infinite potential, well, wave function is a harmonic function. This one is an harmonic function. It's not at all harmonic. Okay, harmonic means sine, cosine, and then exponential function of imaginary number. This one, you see, it's not symmetry, harmonic at all. Okay, but instead this one enharmonic. Second point is that this one not on the wall, right? On the wall. Here is not. Okay, not here. This one not somewhere, right? Not on the wall. Okay, note is not on the wall, and enharmonic wave function. Okay, so this is energy level finite, number of energy level that's finite. So we just finished showing equation for one dimension, that you find wave function and then energy, and then you already analyze the wave function and then energy to understand behavior of particles, right? I said higher excitation, and then of course electron moving so harder, right? Then you understand behavior electron. And also energy level discretize mean based on the film, and then some place you have electron, another place you have electron, another place you have electron not continuously moving, instead they will jump from one place to another place to another place, making a jump, okay, when they absorb energy. So probably you understand behavior of system based on energy level and then wave function. Okay, but you will see we have to calculate
Vẫn còn màu xanh.
probability
Đấy.
of
Đây,
finding particle, or this one is probability density. Okay.
Bởi vì là đội hồi
Psi
đấy
square.
tôi nhớ 7554 tôi có sang bên.
So this one is psi function. Psi function. Now you have to calculate square of this one. So square is of course positive, still positive, but negative become positive after calculate the square. This one, when you square, of course, it will continue having the form very similar, the shape very similar to the first step. This is the wave function, but if you square, the positive part will very similar to the wave function. However, for negative part, now if you square, it will go to positive. So it means the wave function like this, after squaring, you will feel like something like it's go up here, go down little, touching the slash, the dash line, and then go up high again, and then going down like that. That is psi square, right? Very similar. You can remember, go high here for square function, go down and then go up again, and then go down, then go up again, okay? So never have a negative part when you square function, right? Square the wave function. So hopefully, if you understand behavior of the psi function, then you can estimate the psi square easily. You can draw figure, and then you can answer many questions, okay? And then exercise you can fulfill. Okay, so this one, for first step you see like this, and then this becomes square, will be the boundary. If you calculate the integral, this one, integral, okay, of the psi function, then usually this one is you should find the integral equal the area. The area making by this boundary with horizontal axis. So that integral actually will entire this area. Okay. So now if you scan from 0 to A, of course this area should give you equal 1. So for example, if you find one question like, please calculate probability of finding electron from 0 to A over 2. And then of course you just divide A over 2, and then you see half of the area you obtain, and then you can estimate probability of finding particles from 0 to A over 2 in the infinite potential, where energy should be 0.5, right? Probability should be 0.5. All of this equal 1. But half of the area, of course, 0.5. Yeah. So this one is first excited state or second state. Should be first excited state. Now, if you want to calculate, for example, from 0 to A over 2 and probability of finding electron in the second state,
alo
okay, it should also 0.5. However, now if you want to calculate something like this, probability of finding electrons in the second state from A over 4 to 3A over 4. Then you also can see, okay, cut this one half, then of course you should also estimate probability also 0.5, right? 0.5. However, if you want to calculate A over 4, 3A over 4, but probability of finding particle in the third state or second excited state, then what is the value? Then of course very difficult to estimate, because A over 4 somewhere here, and then 3A over 4 somewhere here. Very difficult to estimate. You have to write the expression. and then perform calculation. You will receive the value. Okay, something like difficult to estimate, and then you have to perform calculation based on integral calculation. But otherwise, I think you can estimate based on the area that you can obtain, okay, from psi square. Then it's very quick. Okay, anyway, this one is the first example. So please have a short break. Then we return here and study again. Okay, so please return here at maybe after 7 minutes later. Okay, 7 minutes. Okay, see you then.
Infinity Ward đang nghiên cứu để đưa vào nhiều cách để bạn có thể trang trí cho tài khoản Activision của mình hơn. Cùng với đó, ông lớn này cũng đang tìm hiểu về việc đưa NFT vào Call of Duty, song không rõ là theo cách nào. Năm ngoái, Ubisoft đã bổ sung NFT với cái tên Ubisoft Quad vào tựa game Ghost Recon của họ, song nhận về phản hồi vô cùng tiêu cực. Ngoài ra, đội ngũ thực hiện Stalker 2 cũng đã công bố kế hoạch của mình về NFT, song sau đó đã phải hủy bỏ vì bị phản ứng quá mạnh mẽ. Có vẻ như các game thủ vẫn không có hứng thú với công nghệ này, điều sẽ gây khó khăn cho Activision nếu họ muốn mang NFT vào Call of Duty. Fire Sprite, studio được Sony mua lại vào năm ngoái, đã phát triển một tựa game AAA chưa từng được công bố. Được biết, game sẽ thuộc thể loại kinh dị dành cho PlayStation 5. Thông tin này được hé lộ thông qua một bản thông báo tuyển dụng ngay trên website chính thức của nhà phát triển. Fire Sprite hiện đang tìm kiếm nhân tài cho vị trí giám đốc sáng tạo cốt truyện để tham gia dự án game AAA kể chuyện phiêu lưu kinh dị sử dụng công cụ Unreal 5. Hiện vẫn chưa có thêm thông tin chi tiết về dự án. Giám đốc sáng tạo cốt truyện sẽ chịu trách nhiệm về phong cách tường thuật cũng như tham gia xây dựng vũ trụ của trò chơi. Ứng viên bắt buộc phải có kinh nghiệm ở mức kỳ cựu trong việc phác thảo, chỉ đạo lối kể chuyện. Ngoài tựa game kinh dị AAA đầy bí ẩn kể trên, Fire Sprite cũng được đồn đoán là đang thực hiện một tựa game Twisted Metal mới. Cùng với đó, họ cũng đang phát triển Horizon Call of the Mountain, game spin-off dành năm. Hiện vẫn chưa có thêm thông tin chi tiết về dự án. Giám đốc sáng tạo cốt truyện sẽ chịu trách nhiệm về phong cách tường thuật.
Okay, let's return class. Okay, so now I want to introduce the second application of quantum mechanics in this lecture series. So we will talk about tunneling effect. What is the tunneling effect? So first you have to consider what happened in a very big world. Okay, and then we will introduce about small world. Okay, so big world, for example, if you have the hill, okay. If you drive the car and you intend to drive the car over the hill, right? So if you just provide enough gasoline for the car to run only up to this point, and then of course the car will stop there, okay? Cannot overcome the hill, right? That is very normal. Big world system. So if you have a vertical barrier, for example, the wall. If you already watched racing motorbike on a vertical wall, right? You can see that running. For example, you can have a motorbike, right? Okay, go up high to here. But if no more gasoline, no more energy, and then of course, okay, the motorbike will drop and return to lowest position. This is very normal. Big world will be like that. However, for very small, tiny worlds, just like particle level, then, for example, if the system does have enough energy up to this point, but you still can find the system on this side. For example, electron is just enough energy to hit this point, but you still can find electron on this side because electron can penetrate through the barrier to go this side. Or electron fly from the left to right, hit the barrier. But if the barrier is thin enough, then usually you can find electron on this side, okay? So that is the tunneling effect. So anyway, maybe you should see this video so you can see the effects that demonstrated by this video. What is the tunneling effects, and then how we can apply it in reality. So usually many, but probably I will mention about application so that you can imagine what is tunneling effects and where we can apply to. Okay. so I hope you understand this video. Okay, so you can imagine here you have a source of the wave, for example, electronic wave or electron, okay, project on the barrier. So when the barrier very thick, all of the electronic wave will return, okay, reflected on the barrier and then return to, okay, original medium. However, now if you reduce the barrier, okay, reduce the barrier thickness, and then, okay, the wave, electronic wave, okay, part of electronic wave will return, part of electronic wave will penetrate the roof, so go to different side, and then when it become thinner, all of the wave will penetrate through the barrier. So we have a tunnel effect, okay, and then this one you can find in okay, many applications. For example, in the scanning tunneling microscope, okay, scanning tunneling microscope. It means you can take picture of the material surface by using this technique. So you know, probably very difficult to see detail of the material surface by your eyes or by camera, normal camera, right? Difficult, impossible. But we can use tunneling effect technique to capture the detailed surface of material. So now high technology, of course, should be very high controllability. You should understand very detailed in which location is what atom, what kind of atom, how to grow it exactly, okay? And then you will have a very, okay, something we say small size system, and then you can control behavior of each electron, okay, in that system. Therefore, okay, you have to understand surface of material very detailed so that you can grow material as, okay, we expect. Okay? So how to do it? So usually you see that the this one is the tip. The tip is mean one needle of metal. So if you just scan, okay, over the material surface, remember, scan over, not touch. Okay, the tip here does not touch the surface, does not touch, but always have a distance from the material surface, a distance again. Okay, so when the tip scan over surface like that, and then you know, you just bring the tip closer to surface, and then even the tip does not touch the surface, but electron from material will penetrate through the air or the vacuum. Electron will expand and then go through the vacuum and then try to catch or to touch the tip. So when electron wave touch the tip, then inside the tip we have an electrical signal. Okay. So the feedback system will record the feedback electrical signal. Okay. And then they can reproduce on the surface, reproduce electric signal on the surface like this, and then you can understand the detail of the surface structure, okay, by analyzing electric signal that's sending through the tip. So this one in Vietnamese, you can say this one is chụp ảnh quét xuyên hầm, kỹ thuật chụp ảnh quét xuyên hầm. That will very helpful. Okay, will be very helpful for you to use this one to capture the detail of the material surface. And then once you know how to grow atoms on surface, and then of course you will design many small system, electronic system that have a very high performance, because you can control as you like, right? So it should be very good. So this one is one example related to tunneling effects, but probably you also having something like transistors in computer. So hopefully you are using computer, you using laptop. So computer should made up many transistor in the CPU, also in the in the storage system, also using transistors. Okay, and transistor is very extremely small, that you can integrate many billion transistor, only 1 centimeter square of area, very much. Okay, many transistors, and then transistor very small, so that the transistor can allow us to control 1 electron behavior, allow electron to come in, allow electron to go out, or keep electron inside the transistors. And then you can flip the state of electron, become up or down. So if you have enough electrons, 8 electrons, and then you can encode just like 1 bit of data, right? And then of course in the transistor we should use the tunneling effect, that you have to design 1 layer of oxide, so that you can allow electron come in, go across the tunneling layer, can go out or store inside. So store inside the transistor, it means we store the data. Okay, we already store the data. But if you let electron go out of transistor, of course you erase the data, something like that. I don't have enough time to introduce so detail about the applications of something already mentioned, of examples like that. But yes, usually in the extensive course of quantum mechanics, I will spend my time to explain very detailed how they work. And then anyway, this lecture series is only something very fundamental, that I just want to explain something very basic and not something very subtle. But anyway, if you have a time, please spend the time in searching what is transistors, and then how you design and program electrons to store inside the transistors, something like that. It should be very helpful to understand high technology, and also computer science, and so technology. So anyway, we always can use Schrodinger equation to understand electrons behavior. In the case, for example, the tip and scanning tunneling microscope. So you can imagine the material surface. We have material surface. On the material surface should be the air or vacuum. Let's imagine vacuum. Normally, electron just stay inside the material and not go out, right? Not go out to vacuum space. So now you have the tip. When the tip very far from surface, it means the air gap or vacuum very large. When the vacuum very large like that, it means potential extremely high. potential for electron motion should be extremely high. Okay. However, now if you bring the tip closer to the surface, closer, it means the vacuum space now become narrower. Okay. When it's narrow like that, the potential will decrease, and then electron easily can penetrate through the vacuum and then touch the head of the tip, okay? tip TIP, okay, tip of the scanning tunneling microscope. You can imagine like this. This side is the material surface. Electron will inside the material. Okay. Now, if the vacuum very large and usually potential become very high, okay, very high, and then very thick area, very thick, very high. Now, if you move this one is the tip area, okay. Now you bring the tip closer, and then the vacuum become narrower. So, and then A, of course, becomes smaller, and then smaller, thinner, right? But the potential also can maybe decrease if you move the tip closer to surface, like that. So our target is to understand behavior of electron inside material, electron inside the tip, and then electron in the vacuum or in this region, okay, where the potential, yes, let's say should be finite and U0. So if you use the potential to describe the potential energy for electron to go from left first region to second and then to third region, okay, you imagine electron run from here to here, cross second region, then usually, okay, you have a different wave function. Right? Then of course you have to first write potential on this side. Electron should zero potential because electron freely move inside the material, and this side electron also when touch the tip, and then of course freely moving inside the tip. But this side, okay, electron suffer a potential U0, okay, in this region 2. But our target is to calculate transmission coefficient. That is the square of psi 3. This means wave function in the third region. Square, you will have a probability of finding electron in third region. Divide by probability of finding electron in the first region, okay, first region. Then, yeah, you will see that you just have to calculate A3 over A1 and then square. So this is the target. Before going to perform calculation, we just make a simple description about the wave function. For example, on in the first region, electron freely move and then having behavior of harmonic function. Okay, harmonic function. When hit the barrier, the wave function quickly decrease the amplitude as a exponential function, decrease quickly. When the wave function is hit to the right side of the barrier, the wave function become harmonic again, okay, harmonic again, but with amplitude much smaller than amplitude of, okay, the wave function in the first region. Okay, so this harmonic, this also harmonic, but the amplitude decrease in the middle range should be exponential function form. Okay, that is qualitative description. But detail about expression, you will see, we just follow exactly the step that we already used to solve one-dimensional infinite potential. Well, the first example, okay, we already did. So now you just write Schrodinger equation first, second, and then third region. and then you expect to find wave function in the first, second, and third region should be like this form. And then you have to apply the continuous condition at the boundary for the wave function between first and second region, and then second and third region, and then we say derivatives, first order derivative position also should be continuous. So based on that, you will based on continuous condition for wave function, and then first derivative with position so continuous, then you can write this equation, set of equation, system of equation, where you will find parameters or amplitude of the wave, that is A1, B1, or A2, B2, A3, something like that. Okay. So to make calculation, you have to solve following step by step like this. The calculation lengthy, but already listed in this slideshow, and then hopefully you can follow. But at the end, you have to obtain A3 over A1, okay? And then you will calculate the transmission coefficient. What is transmission coefficient? Transmission coefficient is mean probability of finding electron in the third region when you compare to the first one. It means how much percent, how many percent you can search for electron in third state, in the third region, already penetrate through from 1 to second and then to third region. Right? That percent, say 4% or 10% or 15%. Of course, the percent higher, coefficient, transmission coefficient higher, and then we should know the percent that electron can penetrate to the third region should be higher. Right? So you will see this result, and then this. Okay. At the end, you should obtain this result. But you know probably this one is the expression to calculate. As long as you have parameters, for example, A is mean the thickness of the barrier. So usually you will know thickness of barrier. For example, we have metal surface, you have the tip moving closer, and then of course you should know the air gap or vacuum distance from the tip to surface, right? You always know this one. What is the M? M should be the mass of electron. So electron when fly from left go, and that's of course you should know the mass of electrons. U0 is mean the barrier height, how hard, how difficult based on the energy that electron have to overcome. Then of course you have a barrier depend on the nature of the environment, with the air or some kind of material or the vacuum, and then of course U0 should be different. And then E is the energy of the electrons. Okay, we know this dependence. And as long as you know parameters like that, usually you can estimate is there any possibility for electron to go from metal surface to the tip of the scanning tunneling scope or not. So this one is the expression, but if you want to understand, say qualitatively understand behavior of the transmission coefficient on different parameters, of course, I just want to give you the explanation. So maybe I will ask you, the something we say the qualitative property of the dependence of t on different parameters. Of course, this explanation should be very important when you want to answer theory questions when you do final examination. Don't forget, okay? So I just want to give you one example, not for the particles, but I want to use the big size system and then making some kind of, we say, physical intuitive from big size system you can borrow to small size system to microscopic system. Okay, so now you consider this just like the barrier, the wall, okay, the wall like this. You just imagine some family build very big, very high walls, okay, preventing from outside, okay. You can imagine like that. Now there is one person. Instead of electron, I take the example that is one person. This is the electron, okay. Anyway, you can imagine this is one person. Now he tried to overcome this barrier, but he has energy E, and then he has the mass M. He knows the wall now thickness is A, but the height of the wall is U0. Okay. Now the question: how the transmission coefficient or percent that he can be on the right side? Okay, can be on this right side. He now this left side, okay, on the left side. Now what is the possibility to find him on the right side? Okay, question: what is the depend on U0, depend on A, depend on M, depend on E, then with the T will increase or decrease. So now I just want to ask you the question: what happens if A, for example, U0, U if increase U0, what will be for transmission coefficient? Okay, I want to ask you, okay? U0 increase. What about T? Can you answer this question? U in now, and then possibility of he can overcome the words become more difficult or easier. More difficult or easier? Which one? Do you have any answer? You still hear my lecture, right? Okay, so hopefully, okay, you understand. Anyway, I will explain and then decrease. Because the wall is higher, then he is more difficult to climb over. Right? It's very simple. What the wall is just 0.5, the height is just 0.5 meter height. Then of course, you one step you can over. But now you raise to 2 meter, 3 meter, and then of course he should have to very difficult to climb over the wall, right? Then possibility that he overcome the barrier become decreased. So how about A? The thickness increase. Then of course T will be decreased because you know the wall is very thick. For example, 1 meter thick or same height but 1 meter thick, and then 5 meter thick, and then etc. And then of course you have to see these things. So a lot of energy, and then of course he can overcome the barrier easier. This one become increase. How about the mass? Mass increase. It means now one day he become fatter, heavier, and then of course more difficult to climb over the barrier, and then of course T decrease. Okay, so this is my explanation related to tunneling effect, and then probably okay you have to study it. Then okay, we just finished tunneling effect 5, and then please have a short break. I think 10 minutes, and then we return to this class again. Okay. See you later. Okay, so another example is to solve Schrodinger equation for the particle inside the box of material. So you can imagine this is the one piece of material in 3 dimensions. The electron can move freely inside, not go outside, okay, just inside only. Then potential for electron inside the box, U equals 0, and then you can write Schrodinger equation should be like this equation. So now to solve the equation, you have to use the variable separation techniques. When you separate wave function become 3 different components, x, y, z, depend on coordinate x, y, z. After a few calculation, very simple, okay, calculation, you can convert Schrodinger equation become this form. At this step, okay, E is the total energy of the particle. You can separate become total, okay, energy along different direction x, y, z. So substitute this one into here, and you will try factorize the part depend on x with ex, okay, combined with ex. This one y with ey, z function with ez, and then you will find 3 equations look like this. So now you have to solve the equations, 3 equations, very similar, the same form, and then similar to the case of 1 dimension that we saw at the beginning of the lecture. So we will find wave function like this, and then energy look like this. So now with this wave function, you substitute into here, you will obtain wave function look like this. And then energy ex system use much of a wave function, right? Probably, yeah, that should be a very helpful tool so that you can understand wave function of electron inside the box. However, energy, of course, you can make the diagram like this. So you just substitute n, x, and y, and z value. Of course, you will find E, okay, energy E. For example, E 111 corresponding to set of parameter n, x, and y, and z equal 111. Then you have a one energy level. So this should be ground state. However, for the values like 211, nx equal 2, ny equal 1, and z equal 1, or another set 121, 112, of course, should give you the same energy level. So many set of nx, you see here like 3 set of nx. This means you have 3 different wave function. So different set of nx, ny, and z, of course, you find different wave function. So 3 different wave functions sharing the same energy level, and then we call this energy level is degenerate, okay, degenerate. And then degeneracy order should be 3. So what is degenerate? Degenerate in Vietnamese means suy biến. One energy level, but having different wave function. 3 different wave function. And then you have a degeneracy order, should be 3. Very similar, you have this one. This is a degenerate energy level. This is also degenerate energy level. This is a 6th order of degeneracy. Okay? this state and this state no degenerate, but and the others always degenerate. Okay, so I hope you learn new terms, okay? And then understand how to describe theta. Another example is to understand behavior of electron inside atom. Probably many people will question where is the electron inside the atom. High technology, of course, you have to understand behavior of electron very detailed. Maybe many of you here not study high technology, but you will do different. Okay, so anyway, but we are now in modern life already, and if you not study high technology, of course, not bring much interest to society. Remember. So that's why we learn here. Okay, if you know very detail about behavior of electron, and then you know how to control, and then know how to design, and then of course you can design and then build high technology. Okay, so hopefully Vietnam will have a more percent of science inside, okay, high technology. You need to build electronic system, computers, and many others. Even in the car, you also need high technology. You cannot like just go to buy and buy, okay? But gradually we have to design, to build, to fabricate. Then society, of course, will, okay, increase amount of something we say quality and amount of science inside the product. Okay, so probably hydrogen atom is simplest one, the lightest one, because the locate in the first location of periodic table. So hydrogen atom have only one protons in the center, in the nucleus, and then electron, also one electron moving around. So how to locate electron, where is the electron inside the atom is very important. You can explain many things, okay? And first you have to write potential for electron, right? Electron moving around the nucleus, but what is the potential generated by the proton? So you have to multiply, okay, the product of charge. So you have a proton charge plus E, electron charge minus E. So product of the charge divided by the distance between two charge particles. And then R here, of course, should be the distance, okay, between electron and proton. So you will take, okay, E multiplied by minus E, and then of course become minus E square divided by distance. This means divided by R. And then don't forget, take into account effects of the environment. So yeah, should be 4 pi epsilon 0. If you study in physics 1, you should know it already. So you have potential. You substitute into Schrodinger equation. You should have this wave equation or Schrodinger equation for electrons in hydrogen atom. Our target is to solve this equation, but it's very lengthy, it takes time, so I already provide the supplementary material. Let's take a look to see, okay, where is what is the solution. So basically, in supplementary material, I already shown this function, the radial function, also harmonic function, already having the form available there. So we just pick up and then substitute into here, you should get wave function. Okay, the wave function here, you see this radial function with some parameters, say N, L, okay, parameter, and then harmonic, spherical harmonic function. also depend on parameter, say L and then M. Okay, sometimes we say ML. Sometimes we say this is the ML. Okay, something like that. ML with L in the index. In Vietnamese means quantum number. In Vietnamese means số lượng từ quỹ đạo. Sorry, some number or số lượng từ. How to understand these parameters? Probably you have to remember what you already learned in chemistry. Probably you remember electronic configuration. 1 S2, 2 S1, sorry, 2 S2, 2 P6, 3 S2, 3 P6, 3 D10. So now you will match the letter N. N should be 1, N should be 2, N should be 3. So it means N will give you the cell number. N can be 1, 2, 3, etc. And then this one is the cell number. What it mean the cell? So we have a Bohr model for the atom. This very simple model, but probably very helpful for you to imagine what is happening inside the atom. First, you just imagine this is the nucleus, and then now you have a first shell. First shell is mean this is the orbital for electron to locate. It means the space around the nucleus that you can find electrons. So 2 electrons locate in 1 S2. Okay, this is the first shell. Now go to second shell. Second shell is mean you have a 2 S2 and 2 P6. So each orbital will have 2 electrons. So 2 S2 is mean 2 electrons in orbital S. You can draw something like this. This is 2 S2. And then you draw something like 2P, PX, 2PY. And then 2PZ, something like that. So basically you have something like 1 S2, and then this is 2 S2, and this one is PX2, PY2, PZ2, and then of course all of this one become 2P6. So combine this one, you have a second shell. Okay, this is N equal 2, this is N equal 1, and then etc. You have a next one, you have a third shell. Okay, and then etc. Just try to describe like that. First shell, second shell, and then you go to third shell with many orbitals. So this one we say this is the shell number. Shell number 1, shell number 2, shell number 3. This is shell number 1, this shell number 2, and then next will be shell number 3. So this is very simple imagination to describe what is the meaning of the letter N. Okay, that is the shell number. What is the S? What is P? What is D? And then of course this one you call S, it means relate to L, value L equals 0. And then L equal 1 relate to letter P. L equal 3, equal 2, it means relate to orbital D. So D is mean SPD is mean F, etc. It means this one is subshell. Subshell. Subshell is mean you have a main shell here already. Now you break more smaller orbital. You have a subshell. Okay, subshell S, subshell P, like that. In one shell you can break become smaller subshell. Okay, and then that you denote by SPDF, something like that. And then this one, if you give by the number, then of course number L equals 0, 1, 2, etc. And then you can denote by the letter. That should be 0. Then you can denote by letter S. L equal 1, you denote by letter P, like that. So this is a subshell, okay? And then L is the number that will denote for the subshell. And L is the orbital quantum number. But you have here each orbital will correspond to one energy level. And then of course you can draw one horizontal bar like this. For example, this is one S2. This means one first shell with the orbital S, you have 2 electrons, right? S2 is mean 2 electrons, one up, one down, like this. And then this one, of course, you can know this is the ML letter equals 0. But if you have a here second shell 1, 2, 3, 4 orbitals, you can also draw 1, 2, 3, then 4 energy level. So each orbital, of course, corresponding to one energy level. For example, here is 2s2. Of course, 2s, you have a 2 electron like that. And now you have a px. For example, px, py, pz. Each orbital also 2 electrons. And then, of course, you have a 2px2, py2, also pz2, right? But you combine here become 2p6. Then this one m equals 0 or ml equals 0. This one ml equal minus 1, ml here equal 0, ml here equal 1. So this one you call, this one is the magnetic quantum number, describe the magnetic state corresponding to each energy level. Okay, so I hope you will understand this parameter. So once you substitute these parameters into the radial function and harmonic function already given in supplementary material, usually you can search for the wave function. Okay, exactly. Okay, so you will know what should be the wave function for the electrons in hydrogen atom. So, but energy or shell number, okay, n equal 1, 2, 3, etc. But you also can denote the shell number by using symbol. In the exercise, you will see this one. So shell symbol denote by capitalized letter K, L, M, N, O, P. It means corresponding to value n equal n equal 1, 2, 3, etc. So this is a shell letter. So shell 1 letter K, shell 2 letter L, shell 3 letter M, something like that. It means 1s2 energy level denoted by letter K, okay, etc. But subshell corresponding to value L equals 0, 1, 2, 3, subshell letter, we can use a symbol. This is value, okay? This one called orbital quantum number. This one you will denote like letter S, P, D, F, G, H, okay, something like that. So it means electron inside hydrogen atom, okay, will have a wave function that identify for different orbital. Don't forget, there are many possible orbital around nucleus, but maybe electron at some specific condition will locate at one state or occupy the real space around the nucleus, some specific position, specific orbital. But you know, of course, when solving the equation, you have to not only find the wave function but also the energy of electron. The energy of electron around the hydrogen nucleus very simple. You just see n, okay, n equal 1, 2, 3, etc. So if you substitute n, of course, you can calculate energy of hydrogen of electron, okay, in hydrogen atom. For example, E1 equal this value, E2 equal this, etc. So this one is the energy of electron at the most stable state, and normally if hydrogen in neutral state, the electron will stay at this place. However, now, so first you see energy of electron in hydrogen atom is a discretized, okay, energy level. And then of course in the space you should also locate just like 1s state or 2s, 2p, like that is having many different states. So this one is for 1s, this one is for 2s, 2p state, and this one is a third shell layer, right? Third shell energy level. Then of course also some kind of location inside the atom also separate like that. So it means electron not run continuous around hydrogen around nucleus of hydrogen atom, but something that locate at some orbital, and then maybe if get excited by shining X-ray or something on hydrogen atom, electron will jump to higher energy level. Okay, if electron absorb photon, jump higher. So to higher state, electron return lower state and then emit photon again, and then you see the spectrum. You can see color, red, green, blue, something like that, or even our the spectrum. Then we can measure by machine. Okay, so I have to say, okay, you should learn the rules how to start from value n. You can calculate L and then ML. Okay. How to calculate? If you have a n equal 1, 2, etc. Okay. L will calculate by this rule 0, 1, 2, 3, etc. n minus 1. ML will calculate by 0, etc. plus minus L. Okay. So, for example, if you have an n equal 1, and then you can calculate L. N equal 1, you substitute into here, you have 1 minus 1 becomes 0, and then of course L just receive value 0. L equals 0, you substitute into here, you have ML equal plus minus 0, it means ML just receive value 0. Now n equal 2. n equal 2, substitute into here, you have a L equal 0 or 1. 0 or L equal 1. If L equal 0, substitute into here, you have a ML equal 0. L equal 1. L equal 1, you substitute into here, you have a ML equal -1. ML equal 0. ML equal 1. So now, if you combine then of course this one with this you have a one-way function with set of parameter 2 0 0. You combine these with this, and then of course you have a wave function with set parameter corresponding. This is 1 and then -1, 2 1 -1, 2 1 0. And then this one corresponding to wave function is 2 1 1. So it means you have a 4 different wave function, 1 wave function, 2 3 4, corresponding to the first to the second shell, and then of course it should be 1 2 3 4. You have a different 4 wave function describe the second shell. Okay, then this one, right, you can easily find wave function for it, for electron in the second shell. So this one, okay, why you find this wave function. So second shell energy equal minus 3.4 eV. So this one only one energy level, but sharing with 4 different wave function. Therefore, degeneracy order should be 4. So second energy level degenerate at the degeneracy order 4. Okay? And after that, of course, you can calculate probability of finding particles around the nucleus of hydrogen atom. But this one gives you very simple rule. Wave function, electron in 1s state. This one is nucleus position, and then usually the wave function of 1s very close to nucleus. The nucleus have a positive charge, electron negative charge, so it will very attractive, and then the wave function go very high, very sharp, and then cannot extend away, just very shrunken, something like close to nucleus position. But for another for other states, just like 2s, 3s, 3s, something like that, this will expand, and then go far and far from nucleus. Of course, the wave function expanded. So when the wave of this atom expand, another way another atom also expand like that. It's go to cross like this. When it's cross like that, overlap like that, we can make bigger system, and then you have a solid system, very large solid system, and then also a gas system like that, make bigger system. Okay, so this is the way of how quantum mechanics can explain how to form bigger material based on interaction between electron and nucleus, one atoms to another atom. So anyway, position of 1s, 2p, 3d, 4f can calculate by this formula. Remember, 1s, not 2s, not 3s, not 4s at all. Okay, 1s. First shell should be related to s subshell. Okay, 1s. Second shell should be orbital p. So 2p, 2p, 3d, 4f. Otherwise, you cannot apply this formula. And r equal n square a, with a is more radius, or you have a 0.53 angstrom. N square is mean n here equal 1. For 1s mean you substitute 1 to here, and then you will know position of 1s state at about 0.53 angstrom from nucleus. If n equal 2, and then you have a 4a, it means 2p state at the position, okay, about 2.2 or something like that angstrom. Very similar, you can calculate for different position of atoms around nucleus of hydrogen atom. So as I already explained, if you shine X-ray onto hydrogen atom, you can make electron absorb photon, and then if that photon energy matching the gap here, and then electron will jump from lower to higher energy level. At higher energy level, electron is not stable. Electron will make transition to lower energy level. Okay. So all the transition of electron from higher energy level to the ground state, then the energy gap here is very large, and then can emit energy with emit photons with very short wavelength in the violet region, ultraviolet region. So I hope you still remember the spectrum that I shown at the beginning of this lecture series when we study about electromagnetic waves. So do you see this radiation? Okay, photon emitted can have a wavelength in ultraviolet region. You cannot see by your eyes, but you can recognize by machine. So this one is a Lyman series for hydrogen emission, but you also have a visible range and infrared region. So usually hydrogen atoms. So you just, for example, you contain hydrogen gas inside the glass tube, and then now you can shine X-ray, or you can connect the glass tube with two terminals, two electrodes. And then you just connect with electric power, and then you can establish the electromagnetic field inside the glass tube, and then you can excite hydrogen atom to emit the radiation. Okay, so all the transition from higher energy level to second energy level, this is a Balmer series, and then this is visible series. So you can see the color red, green, blue, something like that. But for different series, transfer to electron transit to third to fourth to fifth state, then can emit photon that will have a wavelength in infrared series. Okay, infrared series named Paschen, bracket, and Pfund series. How to calculate wavelength and energy of photons emitted by electron transition? You just calculate the energy gap. Just take energy, this one minus this one, and then of course you have an energy gap. Okay. So I hope you still remember expression formulated by Einstein photon theory. You can calculate energy gap easily, but you know epsilon equal hc over lambda. So epsilon is energy of photon. H is a Planck constant. C is speed of light vacuum divided by lambda. Therefore, you can calculate lambda equal hc divided by epsilon. So by such way, you can obtain the wavelength for the photons emitted by electron transition. Okay, so I mean, lecture today that's the end at this point. Next time I will continue and introduce about spectrum of alkali metal atoms that can borrow from hydrogen atom. Okay, so I think okay, lecture today just finished. Do you have any questions? I can answer you. Okay. So it means you learn quantum mechanics, of course, more difficult than the others. Even Newton mechanics, you still feel something difficult, right? Even you describe about yourself, you also feel difficult. Then of course you understand, try understand something other than you, and then of course more difficult. So sometimes some people may not succeed in describe objects, big objects. So no wonder when you try to describe something very small that you cannot see, of course more difficult. But people have to believe what already described, because based on what already described, people already control electrons. For example, you can command your laptop, your computer, exactly what you want. But the controlling there based on the control of electron states. Then of course people already succeed in control electron state, right? At first people not believe in what is atom, but gradually they believe that material form of atom. And then they also next they will not believe that atom have proton, neutron, and electron, but they have to believe, right? Now electron you can control behavior. That's why you can command your computer, your laptop as you want, right? You click there, click here, you open this and then control this. You can type, you can read, you can talk, a lot of things, right? You can camera. So you know that is the way of how people understand very deep about behavior of electrons, and then I hope you also understand it. Okay, not difficult, not easy, but gradually you will feel familiar with it. And I hope okay, in this lecture series, call your attention to high technology. Okay, not try something simple. For example, if you do something design mechanic system. The mechanics without electronics is not high value. Okay, don't forget. You have to use electronic system to control it as you want, and then perform high efficiency automatically. But many times you don't have to touch, but you still can make it work, right? And then high technology contribute very high value to our life. Don't forget that one. Okay, so even difficult, try your best. Then maybe someday you will become very creative. Very creative. You can do something more than what other people cannot do. Try your best, please. Do you have any questions? Okay, so anyway, if no more questions, then see you next time. Okay.